Okay. Record it. Be careful what you say, okay? Record it. Okay, so I'm going to talk about KKR-CPA and the extension. For those of you not familiar with it, so it would be much helpful. Much helpful. This is kind of summary with what average electronic structure calculation takes. This kind of loops. First of all, we solve the Kkcp equation, right? This is Schrödinger equation like expression, and phi alpha is called a Kkcp orbital, and the VEF is a one electron potential, right? Including Hodge potential and the extended correlation potential. This all I assume that you're all familiar with this expression. And we take atomic units here. That's why this H pi doesn't exist. ME is all just disappear because we take these units. By solving this equation, this is most kind of abelian method take this kind of approach. By solving this equation, we construct charge density, electron density, and then we check if this density is compared with the previous iteration, if that converge or not. If not, we solve this construct a new LDA or GGA potential, and then feed back into this Kkcp equation and solve it iteratively until it reaches convergence. If it is converged, then we calculate the ground state energy, which is the many body total energy. That's many body equations, the energy. So that's kind of based on density functional theory. That's what we get. This expression may feel a bit strange from what you see in other approaches, because in other approaches you have like total kinetic energy plus U plus this one. But here I did some cancellation because the way kinetic energy is calculated is by sum over the band energy minus the rho times the V, and then end up having this expression, but they're all the same. Okay, so this is kind of total energy. So we calculate. So this is kind of this is all the abelian method takes this kind of loop over solving this this kind of self-consistent process. It takes this kind of loop. So there's different abelian methods. They all differ in a way to solve how to solve this this Kkcp equation. There's one unique method is we're not solving this equation. We calculate the Green's function for this equation. Okay. So this is the kind of approach we take. We're not really solving this equation because solving this equation requires that psi to be calculated and normalized and orthogonalized. But on the other hand, if we can find the Green's function for this equation, we can achieve the same goal because we can, based on Green's function, we calculate charge density. Okay. All right. So the Green's function approach is built in a framework of so-called multiple scattering theory that there is a very there's a kind of analytical form of the Green's function for the Kkcp equation, where the z is you pick up if you want to ask what's the Green's function in certain region. What you calculate is for that particular region around the atom. This is a single site problem, right? You calculate the single site solution. It's a regular solution, and J is irregular solution. Tau represents the multiple scattering equation, multiple scattering matrix. It's a scattering matrix. So the Z and J here are calculated based on the potential contained in this little region which contains a particular atom. So this is a single site problem, single site potential. It can calculate single site Z and J's. These are not block waves. They're not like Kkcp orbitals. Okay, it's not like a phi we've seen before that represent the entire crystal property. But this one is only for single site, so it can be easily calculated based on whatever the potential given in this region. And then the other thing we have to do is for the crystal feature is contained in this tau, the multiple scattering matrix. It is constructed by calculating the single site T matrix. Okay, given that single site potential, you can calculate T matrix. Okay, so I'm not going to talk about how the T matrix is calculated, but we can tell you more about it in the future. But just remember that given the V, single site, single V for particular atom, you can calculate the T matrix for it. And then take the inverse of the T matrix, you put it on at the diagonal block, and put all the off-diagonal blocks are the so-called structure constant matrix, it's related to the location of the atoms. It's a geometrical property. Okay, has nothing to do with whatever potential is. So this can be G can be easily calculated. These are geometrical related quantities, and putting the off diagonal, and I take inverse. You take the n block. That will give you the tau n. Okay, so this kind of related to has the information for the entire crystal. The n is the number all the atoms in the crystal. Okay, so you take all these things for the crystal feature. You take is contained in this form, and take inverse and take a n block, give you tau n. The single side feature is in Z and J for given particular atom. So by this construction, you can calculate Green's function for the Keynesian equation. And once this is called a M matrix. Okay, so once you have the Green's function, you integrate the Green's function from the negative infinity of the energy to up to Fermi energy that give you the charge density. Or integrate the R, you get a density of states. Omega n is the domain of the particular atom. It can calculate the density of states for that particular given atom containing that little region, the domain. Okay. Okay. So this is kind of approach based on Green's function approach. All right. So of course you can say, okay, our crystal is infinitely large. This kind of calculation is kind of mathematically is right, but I think it's not practical, right? So fortunately, if the system is periodic, if there's periodicity that each atom, each site is the same, right? Of course, we can extend it to like a multiple atom planar cell case, but it's easy. But let's consider a simple case that it's a simple crystal that each atom is the same, right? So the T matrix on each side is the same. So if that's the case, you can do some lattice Fourier transform. You end up having equation like this. That this is tau. You have this expression. This tau n turns out can be calculated using this formula. It can work out by using algebra. Just you can easily derive it. So it's not very difficult. So end up that if the system is periodic, you can calculate this tau matrix using this Brillouin integration method. Okay. So this has become a practical. In practical, for you have a unit cell that we usually calculate this way. Okay. But for a real space approach, that you can take this kind of form, but you can make certain approximations to ignore those very long range scattering effects. That's what forms the basis of LS-Math method. This is kind of a case-based method that you consider that it's a periodic crystal. You include all the effects for the entire space, then you end up having this have to do case-based integration. And for this kind of approach, you don't need to calculate Keynesian orbitals, and so there's no need for calculate band structures or that kind of things. Okay. So this is the kind of unique feature of this method. So because it involves calculating integrated over the Green's function in energy, because when you calculate charge densities, so all you have to do is say have a deep core, semi-core states, because this is all electron method, and there's a valence states, right? And so because we calculate the charge density is charge density for the core states plus charge density for the valence states. The total energy is the U plus exchange correlation energy plus this is the kinetic energy. Kinetic energy in the planar method, usually you apply this Laplacian square to the wave functions, because we don't calculate wave functions in Green function method. What we do is we calculate all the band energy and the core state energy and minus rho times v. Okay, that's a different way of calculating Laplacian square and integrate over the space. So this is another way of doing it. So that's what we do. Because we don't have the wave function, that's why we take this kind of approach. Because we know how to calculate rho, right? V effective is already, we know that. So this is how we do the calculation, okay? So the rho itself, the density of states, and times epsilon, and this is kind of integrate over the Green's function. Okay, this is what we take. So it involves integration over the Green's function. You go like this. Okay, you take the contour integration. The reason we do this kind of Green function is analytical. so we, in principle, should integrate from the epsilon B to film energy. Epsilon B is the bottom of the valence band, but we want to avoid the poles of the green functions, because band structures are the poles of the green functions on the real energy axis. Instead of integrating along the real energy axis, we integrate along the contour. It's numerically it's easier to do, so we don't need many energy points to do the integration. We only need like a 20 or 30 number energy points on this contour to run integration. Okay, because in the complex plane, this green function is quite smooth. Okay, so this valence density, charge density, is calculated by taking the green function integration from bottom of the valence band to the film energy, and take the imaginary part and times 2, because there's two assuming there's a 2 electrons per state. Okay. Of course, if it's spin polarized calculation, you have to do that for one for spin up, one for spin down. But if it's non-spin polarized, which is multiplied by 2 and divided by pi, the reason it's pi because based on the residual theorem, you supposed to have a pi here, negative, and then you get, this is kind of general, the kind of approach we take. For the semi-core and the deep core states, they are bound states. The bound states is only related to single side problem. So for bound states calculation, we have a clear boundary conditions, because at certain distance away from the atom, the wave function is supposed to become 0. So use that as a boundary condition, you can solve the bound state problem. So we take entirely different approach, not taking a green function approach. We just solve the differential equation. Yes. What's the question? Okay. Yeah. So for core states, we solve the single side bound state problem by solving the differential equations. Okay, because there's a clear boundary condition we can apply. But for valence, because this is the kind of block states, the wave function is not 0 at infinity, but rather it's a periodic structure. That's kind of difficulty everybody have to deal with. So we take a green function approach. That's how we do it. All right. So there's a kind of unique property, unique feature about this multiple scattering theory, that if you have a single impurity, okay, so single impurity is all the atom is the same except that there's one particular atom is different. Okay, so what we can do is you can construct this structure in such a way that everybody is the same, it's pure, it's a perfect crystal, plus the impurity minus the crystal itself. So you can have constructed this kind of structure. So this will give you some idea how to solve this kind of problem. That is, you have a perfect crystal, like one atom pin. This is a simple crystal problem. Everybody know how to do it, but plus this kind of plus and minus things here. So we can calculate T matrix for this single site. It's called a host atom. We can calculate its scattering matrix, and the impurity atom we can calculate the T matrix for it. And you can use the construction I showed you previously in the previous slide for the tau matrix. You can derive yourself. It turns out, mentioned about tau M matrix, how it is constructed. Okay, so that's the way you can do that, because all the T matrix is sitting on the diagonal blocks. You can make this kind of a construction, and finally can prove this formula. It's analytically it's an exact formula. So the way that, okay, this tells you how to calculate the tau matrix for the central side atom related to central side atom is, it is constructed by, consider this a perfect crystal tau matrix. Okay, everybody's the same, so this is kind of perfect crystal problem. So this kind of problem can be solved using this case-based integration method, and multiply by the Ti, this impurity single side T matrix inverse, minus the host atoms, the T matrix inverse. Okay, you multiply together and plus identity matrix and take the inverse and multiply by the host tau matrix again. Again, this tau host is calculated using the case-based method. This is because this is a perfect crystal, right? So this construction will tell you how to calculate the tau matrix for the impurity embedded in a perfect environment. Okay. This idea can be extended to a cluster situation, that instead of one impurity, you have like a cluster of the particular kind of atoms embedded in a perfect otherwise perfect environment. Means by perfect means that all the other atoms are the exact same. Okay, they are perfect. So this can be easily extended. The formula will be look very much the same. Okay. The reason I want to mention this because this is important for the KKR-CPA approach. Okay. Now, I was just giving you some kind of brief summary about how we do in the multiple scattering theory, or our approach to the electronic structure calculations. Okay. Now, come to the average approaches to random alloys. And generally there's three different kind of approaches, right? As I mentioned in the beginning, that the supercell approach, in our particular, I know you have dealing with other type of methods. No matter what method you use, you can just, all you have to do is just solve the supercell problems, right? In our toolbox, we have LSMS method. It's a linear scaling method, allows to study very large unit cells up to like tens of thousands of atoms. And I don't know how many other application methods can really do that. This is really linear scaling. It's at the physics level. It's really linear scaling. Okay, it's not like some few other methods, and they're not really linear scaling. Only linear scaling at certain number of atoms. When number of atoms is larger, that become not linear scaling anymore. But this is a really linear scaling. So we have LSMS method. We can do a supercell approach, okay, to study random alloys. All you have to do is just generate like random structures and do the calculation just by brute force. Another approach like using cluster expansion type of approach, particularly this use a pickup average method plus SQS method to generate a set of spatial quasi-random structures around calculations. Okay, so we can, in our toolbox, we have so-called KKR method that is just designed for calculating a given a particular crystal. We do the KKR method. That's based on this K-space integration technique I mentioned. Okay, another thing I just want to mention that the difference between LSMS and KKR is that the difference in the way to calculate Tor matrix. Okay, everything else is still the same because the only difference is how to calculate Tor matrix. LSMS is a real space method approach that the way to Tor matrix is calculated by ignoring long range multiple scattering process being ignored. So you can form the kind of linear scaling type of way of calculating Tor matrix. KKR is consider that the entire space is the unit cells repeat self fill up the whole crystal. So fill up the whole space. So it takes into account the whole crystal. So it has like a K-space. The Brianzon integration is involved. So KKR plus SQS will be a tool to use for study random alloys. The third technique I'm going to talk about today is called KKR-CPA. Okay, it's an effective medium approach. The way it is done here is that CPA means coherent potential approximation. The idea is how to calculate configuration average of the electron density, for random alloys. Okay, so what happens is, in principle, you're supposed to generate all different kind of configurations, and then take the average. Okay. The idea for the effective medium is it possible to find such an effective medium that we can calculate perform electronic structure calculation for this effective medium. Its property represents the configuration average of this quantity. Okay, this is just kind of particular configuration of a random alloy. You have to run many different kind of configurations and do average. So our goal is to find such a medium. That medium itself, if we perform calculation on that for that particular arrangement for this medium, that give you the configuration average properties. Okay. So the question is, what's the effective medium? How do we find that effective medium? So the nice thing about effective medium is you see all these atoms, virtual atoms, they are exact same. So this is kind of simple crystal problem. So we need to find this effective medium. Okay. So we need to find this kind of virtual atom, what that is. And you can relate that to some kind of like approach, like say virtual crystal approach, right? They try to average the potential, but that's not really a good way to do that. But the kind of idea is very much similar. So we kind of find a kind of average medium that has a kind of feature of being the real crystal being averaged. So that's what we want to find. So the way we do that is we consider this is constructed by assuming that if this one, assuming that you have like two atoms in this binary alloy. Okay, one is atom 1 or atom 2, and the concentration of atom 1 is C1. The concentration of atom 2 is C2. It takes this kind of average. That is, you have atom 1 in the center and surrounded by this effective medium, which we want to find out. We don't know what that is. And we average this kind of systems. Another system is like atom 2 at center and surrounded by effective medium. So we do this kind of average. So this will give you this perfect crystal, this effective medium crystal, right? So this is called single-side approximation. Okay. Now, so from this expression, this already give you some idea how to find this effective medium. Notice that, remember I talked about impurity problem in the previous two slides that show for this kind of a particular structure that there's a single impurity surrounded by otherwise the perfect crystal environment. We know exactly how to calculate this in the framework of multiple scattering theory. Okay, we know exactly how to calculate tau matrix for this particular atom. So once we have that, we can calculate the Green's function for it. Okay, so we know exactly how to calculate the G alpha, the Green's function for this particular atom. Alpha is 1 or 2. Okay, in general, alpha could be 1 to n alpha, depending on how many species in it. So C alpha is the content of the given species. So you do this average. So if in principle, that's supposed to give you the Green's function for this crystal and take the average. So this kind of idea we want to get, we take. Our goal is to find this effective medium. Okay. So once we have the Green's function, we take the average. Then the charge density of the random alloy is calculated by taking the imaginary part of the Green's function and divided by pi. I forgot to multiply by 2 here. Okay, it's supposed to be like a spin up, spin down. Okay, but you get the idea what the meaning of it. So this is charge density. So that's how we calculate charge density. So because all the arbitrary calculating is the goal is to calculate charge density. Okay, then going to the next loop, further get a charge density, charge self-consistency, and then calculate total energy. So how to calculate charge? So that's how we calculate charge density. Okay. All right. This is a so kind of basic idea about CPA, KKR-CPA method. Is we try to find what's the CPA medium. All right. Now, how do we calculate CPA medium? It's a little bit further details. So now we are facing this how to solve this single side problem, right? So there's a particular given atom, alpha, species, alpha, 1 or 2 or whatever, depending on how many species in it. So our goal is to find this effective medium. This is a single impurity problem. As I mentioned in this previous, in a slides back, few slides back, this is kind of tau matrix to calculate for this impurity. Remember, this tau alpha, tau CPA is a perfect crystal with the CPA medium on each side. Okay, we know exactly how to calculate. If we know that TCPA, the T matrix represents for this CPA atom. If we know that, we know how to calculate tau CPA. That's what the expression I gave you back a few slides before, right? That's how we calculate tau matrix for this perfect crystal that every side is occupied by this effective medium CPA, the T matrix for that. So we know how to calculate it. And T alpha is particular this impurity side. The T matrix for it is a given particular atom, the T alpha, inverse minus TCPA. That's what actually TCPA is unknown so far, but that's what we want to calculate. So our goal is to calculate TCPA, this CPA medium scattering matrix. Okay, so that's what we want to calculate. We calculate tau alpha. So far, TCPA is still unknown. Okay. But TCPA needs to be calculated self-consistently by iterating this expression because our goal is to have is find that this has to be true that, but on average, tau alpha on average has to be tau CPA, because this kind of requirement for the Green function average has to be the average of the Green function for individual single impurity problems. Okay, so this is kind of expression will has to be used to check whether self-consistency has been reached. We can, how we found TCPA, we can start with like this kind of average. For this is not a real solution, but we start with this, and then we kind of go through all these procedures, and finally to find whether this is true. Okay, so this is kind of, we have a little self-consistent condition to find the CPA median. Is we start with this averaging T matrix, because we know T alpha, because we know the atom potential for each single given atom. We take average of the T matrix for the potential for the individual given particular atom. We can calculate T matrix, the scattering matrix. We take average of it as an initial guess of the T matrix for the CPA median, right? We use that to calculate tau CPA. Okay, based on the initial guess of it. And but CPA median is required to satisfy this expression. So we use this single impurity expression to find the tau alpha. Okay, that's the equation for a single particular impurity surrounded by the CPA median. So that's the expression I gave you before. And then we do the average. We check if that's equal to this. Okay, but we don't know, of course. In the beginning, it should not be equal, but that's our goal is to reach this. So that's kind of check if TCPA is a convergent, is what we want. If yes, okay, well, then we stop. If not, we go back. We'll have to find construct a new TCPA, and then put it in here and do the calculation. Okay, and you have to figure out how to, from this kind of expression, you can figure out what's the TCPA is supposed to construct it based on. I'm not going into detail, but anyway. So the idea is to figure out how to construct the next TCPA to go in here and go around until self-consistency is reached. So that's kind of TCPA. That's kind of effective median we want to calculate. So we're really not calculating the potential for the CPA median. We calculate T matrix for the CPA median. Okay, because CPA median is not a real atom anymore. There's no potential for it, but rather we calculate scattering property of the CPA median. So the T matrix is what we calculate. Okay. So, and also this kind of iteration takes for each epsilon. Okay, remember that we have to calculate Green function for on the energy contour, and we pick up some points on the energy contour. For each that kind of energy point on that contour, we do these kind of calculations to find what tau alpha is. Then we can calculate Green function for that on that energy contour. Okay, so this kind of calculation takes for each energy point. You can stop me, and if you have any questions.
So the calculation of this TCPA is basically solving a set of linear equations so that this, for your next guess, so that this condition is satisfied, or?
Yeah, this has to be checked. Yeah, this will be satisfied.
Right. I mean, that gives you a set of linear equations that you can solve to get a new guess for TCPA.
Yeah, yeah. I don't think I used to have another slide show how the next TCPA is supposed to construct it. It's a kind of a bunch of linear equations. You just have to manipulate a little bit to take, you know, basically just based on this equation, you have to take TCPA out. It gives you the idea of what the next TCPA is. Based on this equation. Yeah. Yes, go ahead.
And so you have basically two loops. You have CPA loop, and after that, and you have also external DFT loop.
Yes, yes, yes. So that's SDF. That's a charge density self-consistency has to be. Yes. Yeah, that's there. Okay. This one is just inside for the calculation of charge density for itself. You have to take this kind of loop to find what's the effective median.
Yeah, and then you've got a new charge density, which you use to construct a new exchange correlation potential, and then you iterate this outer DFT loop until you've reached self-consistency there.
Yeah. Okay. So what we have next is once we calculate tau, okay, then we calculate the, okay, so once we have the TCPA, we get the TCPA, then we can calculate tau matrix, right? From the previous slide I showed you. Once we have this tau matrix for this particular impurity, this is a particular given atom surrounded by the effective medium, and we can, we know the potential because this is a specific particular atom. We know exactly how to calculate this single site solution, Z and J's. We calculate Green function for it. This Green function represents that this particular atom is surrounded by the effective medium, CPA medium. Okay, CPA medium again represents the averaged effect of the random alloy. All right. So once we have a Green function, we can calculate charge density associated with this particular atom in the random alloy, and the density states of this particular atom in the random alloy. Okay, this is this is an approach we do. This called form the basis for the KKR-CPA, and you can calculate a net charge associated with the particular atom. Right? We know the total atomic number of the atom. We calculate charge density in the domain that atom occupy. Difference give you the extra charge for the atom. Obviously, CPA medium is supposed to be charge neutral. Okay, because the whole crystal has to be charge neutral, so that has to be 0. But of course, it's not always the CPA. It's not always the case, because if you have like a sublat, this is just simple single lattice case. If you have a sublattice, that is, you have a more complicated crystal. Some sublattice is occupied by random alloys. Others are just occupied by kind of given specific atoms. So in that case, that sublattice may not be charge neutral. Okay. But for like a simple solid solutions, charge neutral is supposed to be there, so we hold. In more general case, the unit cell has to be charge neutral. Let's just talk about the simplest case. So this is true. So once we have the rho, we calculate the Hodge potential. Okay. Then we calculate the exchange correlation potential based on given the charge density. We construct effective potential. The effective potential will go back to the self-consistent loop, right? There's the loop I showed at the very beginning about ambulatory calculation everybody performs. Okay, so that kind of loop we take. This we need to figure out how to calculate this V's, right? Effective LDA or GGA potential, but it requires the charge density. Okay, so that's how we calculate. So on average, the charge density is a kind of average of the rho alpha, because rho alpha itself represents a given particular atom, what's charge density on it. But on average, for alloy, on average you can take this average. Okay. Okay. So this is the kind of approach what KKR-CPA is doing. So actually, what is missing in conventional CPA method? So effective medium is determined by requiring the probability of a species occupying an atomic site is irrelevant to its local environment. Remember that we did the average for effective medium equal to C1 times single impurity surrounded by CPA medium plus C2 times the other single impurity surrounded by CPA medium. So basically, that means the probability you find a particular atom at a particular site, the probability is C1. That means based on the content of the species in the crystal, right? But in reality, sometimes if your system is not completely random, sometimes it's depending on what's your environment. If you have like a more or less like short range order effect, means an atom is like to be staying with unlike atoms. Or you have a short range clustering effect, means like atoms tend to stick together. So really, a site occupied by particular species also depends on the what's neighboring environment. Okay, so it's not really. So that kind of there's a short range correlation effect. Certainly, it's missing in the CPA approach. Okay, so that single site approximation has is really good for complete random structure. But if your structure has short range correlation in it, this kind of effect is not included in the construction we see. Okay, so short range ordering clustering effect is missing. Okay, in the way the construction, and there's an effort to improve it. That's called molecular CPA. Unfortunately, that seems like being proved that it's not very efficient to deal with, to implement. It seems like people get it kind of abandon this type of approach. That is, it's not like a single size. It's at given put a cluster or pair or type embedding in the effective medium. This is a very considered as a very inefficient way of doing it. Other approach, like in the recent year, there's something called a non-local CPA, or based on the idea of DCA. I believe Hannah and Carmine had better idea about, they can expand to better how DCA works. There's very recently, there's a cluster average CPA. I'll explain how it works, okay? I'll show how every cluster CPA, how it works, how to include short range order effect. So there's another problem. This one thing is this short range correlation effect is missing. Another problem is CPA medium site carries the same amount of charge, or which for it even is zero if it's for simple lattice. Okay, that's as I mentioned in the previous slide, because each side has to be charge neutral. So that means if a particular site is occupied what given particular atom, it sees the same potential if the site is occupied by different atom. So no matter what it means, no matter that site is particularly occupied by atom 1 or atom 2, it sees the exact same long-range Coulomb potential, because every other site is charge neutral, right? This particular site is atom 1 or atom 2, it doesn't matter. Long-range Coulomb interaction acting on me is the same, okay? So that implies that because every long-range Coulomb potential is the same, so I can take the V out, so basically that's what we get, okay? That implies this. So this is basically, so each chemical species carries a different amount of charge. Remember that as we calculate the charge density, and we can integrate it over the space that particular atom occupies, and you can find what's the extra charge that particular atom carries. That's because charge transfer. You calculate it, but seeing as it sees the same long-range Coulomb potential, also known as called a Manon potential. Okay, for the other, the reason for that, because all the other sites are carry this to the central side. All the other sides has the same amount of charge, or even on average. Okay, so it sees the same potential. That's long-range Coulomb potential. But if you do supercell calculation, you find that's not the case. For supercell calculation, you can plot, you can calculate the charge on each atom, and you can calculate long-range Coulomb potential on each atom. What you see is that they're linearly dependent on one another. That is, the more charge I have for given atom, the more the more the Coulomb potential I feel. So each atom is just acting like a capacitor. That the more potential I apply on me, and the more charge I get. So it's totally different from what CPA is telling you. So that is, this is not equal to one another. Okay, so this is kind of conflict with the CPA picture. From supercell calculation shows that this result. So that needs to be so obvious. The CPA this procedure is for when you calculate effect the new potential. So means that if you take a KKR-CPA approach, even you calculate charge densities, but when you calculate construct a new potential, you need to correct it by adding this property here. because only within a CPA approach, what happens is each atom will feel the same potential from the long range interactions, but that needs to be corrected. So efforts to improve this is called a local screening model or charge correlation model, that they assume that a given atomic species, its charge being completely screened by the nearest atom. So if I have a carry certain amount of charge, the nearest atom will carry an opposite charge, so that further away, the atom sees no effect from the extra charge that particular atom had. Okay, so this is kind of screening model. So if you have this kind of construction, you can calculate what extra potential applies to the central atom and what's the extra energy needs to be added to. So this kind of approach is taken by two groups. One is by Frank Pinsky and Dwayne Johnson, and another group in Europe also take this similar approach. Okay, it's just kind of adding extra terms in calculating effective potential. After you have done the charge density calculation, then you can apply this model and calculate new potential. Okay, and also adding an extra term in the total energy. So that's what they do. Okay. So basically, there's two problems with the conventional KKR-CPA approach. One is this Schrödinger correlation effect is not included. Another is there's a charge problem. Okay.
But Jan, yes. It's still true that, for example, in system when these non-local correlations are weak, that CPA will give you faster convergence than usual supercell calculation. Brute force supercell calculation, because to some extent CPA is treating system in thermodynamic limit. Medium helps with the convergence.
Yes, I think so.
Okay.
Because when you have large unit cell, there's you have a lot of charge going around. You have to be kind of rearrange charges around the atoms. It takes some kind of the larger the unit cell, I believe it takes longer to converge for charge self-consistency. But if you do KKR-CPA calculation, this become only one atom per unit cell calculation. Convergence is should be easier.
So that's actually sort of a good point for very large supercell calculations. Even though, as Yang said, our individual self-consistency step, the effort scales linearly with the number of atoms. We might need for larger and larger disordered systems more SCF steps to reach convergence, to really have the charge properly redistributed through the system.
Mm-hmm. Thank you.
Yeah, just summarize that a conventional KKR-CPA has two problems. One is related to how to calculate effective medium itself. That is related to the fact that the Schrödinger correlation effects not being properly included. The other problem is related to when you construct a new potential for the next iteration, SCF calculation. You need to include this long-range Coulomb potential being properly taken care of, because it really for the construction of the CPA approach, each side sees everybody else being the same. They have the same charge, but in effect, in the supercell calculation, it proves that it's not, because the different species sees different potential, because different species has different extra charge it has. As I mentioned that. The extra potential is linearly dependent on the charge that particular species extra charge carries. So they're dependent on one another. The potential and each species sees depends on the charge it carries. Okay, they're not independent. So this be taken care of. So the two things need to be corrected. Okay, so that's kind of two problems with CPA. All right, so now I'm going to take a mention about how to correct the first problem, how to include Schrödinger order, Schrödinger correlation effects in the CPA. This approach as a result of one time I was talking with Mike Willem. He's a professor in the physics department of Carnegie Mellon. He's been doing random alloys. He initially started with like a quasi-crystal. That's what his approach. His interest. Then he gradually moved on to other disordered structures. Like I remember the first time I worked with him was many years ago. It was on the metallic metals, amorphous metals, and then his focus starts to switch to high entropy alloys. He always doing his big problem is how to study random alloys. But he doesn't use like CPA, this kind of approach. He always does with VASP and plus SQS. One time he was talking to me about, but they tend to use like a average crystal type of approach. Mm-hmm. But they also have the problem how to include joint order effect. So they had an idea about how to average the potentials. Of course, that's not going to work. That when we talked about this, how to include joint order effect, he mentioned that this idea. That, hey, I say, hey, this can be applied to CPA, the same thing. So the idea is that embedding a cluster instead of single site in the effective medium, so that this which allow to include joint order correlation effects. But of course, what kind of cluster we deal with? Because the cluster could be many different clusters, many different configurations, right? So the actual cluster we include is not many different configurations of clusters. Rather, we include the cluster is made up of this given particular species at the center, surrounded by this averaged atom. Okay, averaged atom. The average atom is based on the probability of the surrounding atoms. That probability is given the central atom being alpha. So what's probability? That's kind of conditional probability. What's the probability of the other kind of species will occupy as a neighboring atom? So we average over the T matrix because we know exactly how to calculate T matrix for given atomic species. Because we know the potential for given atom, we can calculate the T matrix for that. So this probability is related to the joint order parameters. So that is we embed instead of like conventional CPA, we embed in particular atom, embed that in effective medium. Rather, we embed this cluster in effective medium. But this is not all possible configuration of the clusters. Rather, it's a particular kind of cluster. But center is still the particular atom, but the surroundings is average T matrix. Okay, so that average T matrix is by averaging different kind of species. The weight is a conditional probability. Okay, so this kind of problem, fortunately, in the multiple scattering theory, it's very easy to deal with. We know how to calculate the tau matrix for that. It's a simple extension of the single impurity formula. You can easily, that's just like this. Okay, it's the same form, except this is it become a block matrix. This T alpha block is the matrix is a diagonal blocks. All diagonal are 0. T alpha is this particular atom T matrix inverse at the upper left corner. All the other diagonal corner blocks are the T matrix of this guy, this average atoms. So that is all the other diagonal blocks are T alpha inverse. Okay, so that's a construction of this T matrix. And this one is just also a diagonal block matrix. The TCPA is in the center. Okay, TCPA inverse at center. Okay. So tau CPA is it's an effective medium. It's a TCPA is everywhere. You calculate that. You can calculate this tau CPA, except this kind of matrix size is the same as large as this. You take that and take the 1-1 block. That will give you the tau alpha. This is kind of general extension of the single impurity problem, so it can be easily extended too. So that's a formula. It's an exact formula, right? So that's just a simple idea. So you can, once you have a tau alpha, then we can calculate Green's function for it, right? We can calculate charge density. So the way the way it is calculated, so that this one will have this Schrodinger order effect being included, properly included in it, and even it can extend the way you calculate TCPAs, that my CPA medium can be determined using this condition, using this cluster embedding. So my CPA medium can be calculated self-consistently to include this kind of Schrodinger correlation effects. So the student is volunteered to work on this. So he implemented because Vishnu, and he's a graduate student at CMU. So he just implemented this idea and in the must. So he wrote a paper on that. So being accepted into a PRB. So you can find this paper online. So he did some calculations. This is a copper zinc. We know copper zinc at the I think we did that tutorial, right? Copper zinc at the ground state is a B2 structure. But if you increase the temperature, copper zinc become BCC, become random alloy. But still, it's a kind of Schrodinger ordering effect should be play kind of important role in it. So if you do a conventional CPA, this energy is dashed line, all right? We use that as a baseline. If you include the Schrodinger order, by the way, we are so used to with Warren-Coley Schrodinger order parameter, which is related to the conditional probability by this formula. Okay. So if we use a different Schrodinger order parameter, we can calculate see how energy changes, right? So this side represents that there's more Schrodinger ordering in the system. This side has a completely a clustering in the system. Clustering means that more copper like to stay with copper, and zinc stay with zinc. On this side is copper like to stay with zinc. Actually, this turns out this has low energy. This is kind of completely random, complete disorder structure. So you see the energy that the copper zinc prefers Schrodinger ordering because it has a low energy. So this approach. And turns out the CPA medium, there's a non-self. Okay. This dashed line. See this dashed line? Effective medium is calculated self-consistently with a cluster embedding. This a red solid line is the we use a conventional CPA medium. We use that as a result. So both actually they are very similar. So it seems like it's unnecessary to self-consistently calculating CPA for the clustering for the embedding cluster. So they are very much close to one another. At least for copper zinc, it shows that. This shows the density of states calculation. It's a bit hard to view, but the student did this calculation. So it shows the Schrodinger order effect, how this changes the density of states. Let me see. So B2 structure, copper. This is a kind of there's more structure in it. This B2 structure is copper, and the red line is a zinc density of states. And for the single side CPA, this is just a conventional single side CPA, is kind of broadened density of states. Okay, this is expected that it's a dot line, and if you have include Schrodinger order effect, and you can view that by yourself. I couldn't carefully review it. So the Schrodinger order effect will, if you do the complete random alloy calculation, you see the kind of broadening of density of states. But if you introduce the Schrodinger order effect, you'll see some structure being built into it and make it more similar to B2 structure. So you see some kind of Schrodinger order effect in it. Okay. That's all I want to talk for this. So let me, any questions? Okay. Let me stop recording, I guess.